33 billion years. You heard that right. That's the time frame scientists now predict for the end of the universe. Currently, our universe has already traveled more than 1/3 of that journey towards its final destination. There was once a belief that the universe would continue expanding forever under the influence of eternal vacuum energy. People used to envision a universe accelerating without limit, but new data tells a different story. Recent research reveals a transformation happening within dark energy itself. If its pressure continues to weaken, expansion could slow down, stop entirely, or even reverse into an ultimate big crunch. This discovery places everything we understand about the universe's fate under a massive question mark. Why 33 billion years? What evidence points to this dramatic conclusion? And what does it mean for the cosmos and for us? As you might imagine, today's journey will take us deep into new research that's fundamentally reshaping the timeline for the universe's end. And this time, it's no longer just empty hypotheses. Results from the Dark Energy Survey and the Dark Energy Spectroscopic Instrument suggest that dark energy may be evolving, deviating from the lambda constant in the standard lambda CDM model. Those data points are gradually painting a new picture of the distant future. Not infinite acceleration, but a trajectory that could slow, stop, and then turn back. Its implications stretch from fundamental physics, particles, and gravity, all the way to civilization's long-term plans, mission visions, intergalactic travel opportunities, and how colonization strategies might change if expansion isn't eternal. So why does it matter so much that dark energy isn't constant? Let's start with a basic fact. The universe hasn't always expanded at today's rate. After the Big Bang, gravity dominated for billions of years, restraining the initial expansion. For most of the 20th century, scientists believed this deceleration would continue and might eventually pull everything to a halt. But in 1998, a shocking discovery rewrote that script. Those distant stellar explosions called Type 1a supernovae appeared dimmer than expected. Dimming meant they were farther away than redshift suggested. The only explanation, and it was stunning, the universe's expansion wasn't slowing down, it was actually speeding up. Imagine a car that's initially slowing down, but then unexpectedly hits the gas harder and harder. Gravity was the brake in that early era, and then an invisible engine started pushing with increasing force, causing the car not just to stop decelerating, but to accelerate. That was the dawn of what we call dark energy, a mysterious force or property of space itself, pushing galaxies apart at an ever-increasing rate. Dark energy is estimated to make up about 68% of all energy in space. It acts like negative pressure, seeping into every corner, stretching the very fabric of the universe. The dominant theory, rooted in the lambda cold dark matter model, holds that dark energy is a cosmological constant, a fixed, unchanging vacuum energy embedded in Einstein's equations. This lambda constant provides an elegant, simple explanation for accelerating expansion, a constant pushing pressure that increasingly dominates as the universe expands. According to this model, the future is pretty predictable. If dark energy truly is constant, expansion will continue indefinitely across trillions of years. Galaxies not bound by gravity will vanish from sight, stars will exhaust their fuel, matter will decay, and the universe will sink into heat death, absolute cold and darkness. That's the big freeze scenario, gradual cooling into extinction. The only alternative then would be an even harsher scenario, the big rip, where dark energy somehow grows stronger over time. In any case, a big crunch, a future where the universe collapses in on itself, seemed ruled out after 1998. Gravity alone wasn't strong enough, and dark energy was firmly in control. At least that's what we used to believe. But scientists kept asking questions. Could dark energy be more complex than a simple constant? Some hypotheses suggested it might evolve or change, a concept called quintessence, where dark energy is a dynamic field rather than a fixed value. Others even wondered if our understanding of gravity itself might be incomplete. These ideas long remained speculative, intriguing thought experiments lacking convincing evidence, until recently. Since then, our technology has advanced dramatically. Over the past decade, two ambitious projects have been deployed to create unprecedented detailed maps of the cosmos. The Dark Energy Survey, scanning the southern sky, cataloging distant supernovae and the distribution of galaxies and clusters. Meanwhile, the Dark Energy Spectroscopic Instrument is precisely measuring distances and velocities of millions of galaxies, creating a vast three-dimensional map of the universe. By charting how universal expansion has evolved over time, these studies aim to determine whether dark energy is truly constant or has been changing. The early results are fascinating. Over the past year, data from DES and DESI have begun indicating that dark energy's influence might be shifting. Subtle patterns in galaxy clustering and the brightness of distant supernovae suggest the universe's acceleration doesn't perfectly match a lambda constant. In fact, the data, preliminary yet statistically significant, shows dark energy may have been stronger in the past and is now slightly weaker than lambda CDM predicts. If true, this directly contradicts the standard cosmological model, which assumes constant dark energy. Recognizing something else might be happening, theorists swung into action. Could there be an explanation for dark energy's weakening? One bold proposal, published in mid-2025, suggests dark energy might have two faces. In this new model, dark energy isn't a single entity, but a combination of two components. The first component is an ultralight particle called an axion, a hypothetical particle, ghost-like, drifting through space with almost no interaction. If they actually exist, axions form a field permeating the entire universe. Their combined energy, though extremely faint, could explain the accelerated expansion we observe today. Essentially, the axion field acts as a kind of fuel for expansion, pushing galaxies apart. The second component is none other than Einstein's cosmological constant lambda, but with a strange twist. In this model, lambda isn't the dominant force. In a surprising turn, it might even be negative. Currently, the positive energy of the axion field overwhelms this tiny negative lambda constant, creating a net repulsive force accelerating expansion. If true, today's universal acceleration is just a temporary phase fueled by axions. However, this won't last forever. As the universe expands and ages, the axion field is predicted to dilute. Its energy density will gradually decrease. In other words, if this holds, we might have the first scientific explanation not just for why the universe might expand, but also for why someday it might collapse. When axions weaken enough, the negative cosmological constant lurking backstage finally takes over. Unlike a positive lambda pushing space outward, a negative lambda works in reverse. It acts like a cosmic tether, slowing space's expansion rather than accelerating it. Initially, this change would be barely noticeable, just a gradual slowing of expansion. Eventually, dark energy's repulsive force vanishes entirely, and gravity's pull, now unopposed and even reinforced by negative vacuum pressure, takes command. Expansion will slow, stop completely, and then reverse. According to this model's authors, on cosmic timescales, reversal could begin surprisingly soon. They estimate the universe's expansion might start slowing within just 10 billion years, less than the universe's current age. The beginning of the end, as they call it, would mark the moment when galaxies that have drifted apart for eons gradually start drawing closer. What follows would be a slow-motion collision on a magnificent scale. Over the next 10 billion years, the universe would contract in a long twilight collapse. Galaxies would merge into even larger structures. Distant clusters would rush together, and future observers would witness a completely transformed night sky. As contraction accelerates, the universe shrinks, matter heating under pressure. Over billions of years, the universe as we know it galaxies, stars, planets would close in on itself. In those final moments, all matter and energy of the universe would compress into an ever smaller volume. Temperature would skyrocket, atomic bonds would break, stars would collide, and black holes would merge. Finally, the universe would end as an unimaginably dense and hot fireball, essentially becoming a new singularity, the mirror image of the Big Bang. That is the Big Crunch. If our calculations are accurate, the total lifespan of the universe would be just 33 billion years, and we've already traveled 1/3 of the way to the end. It's important to note that this remains a hypothesis. The results from DES and DZ inspiring it are still preliminary. Currently, they're just statistical hints needing confirmation. The axion model is one way to interpret the findings, but it's not the only idea being discussed. Another theory is gaining attention, in some ways even more striking. What if the universe isn't as uniform as we think? What if, on the largest scales, it has a slight spin? In mid-2025, physicist Nikodym Poplawski pointed to compelling evidence that our universe might be rotating. Data from powerful observatories, including the James Webb Space Telescope, reveals a surprising pattern. Deep field studies show about 2/3 of examined galaxies appear to spin in the same general direction, rather than randomly. Moreover, these galaxies' rotation axes and cluster movements display unusual alignment. It's as if the universe has a subtle but distinct axis, a preferred direction in the cosmic arena. This challenges the cosmological principle, the fundamental assumption that the universe on large scales is homogeneous and isotropic, the same in all directions. A rotating universe breaks that assumption. Yet Poplawski suggests such rotation could answer some of our deepest cosmic mysteries. He reflects, it would be amazing if a simple rotation of the universe were the source of dark energy, especially since it predicts its weakening. How could a rotating universe mimic dark energy? The idea draws on centrifugal force, the same effect pushing you outward on a merry-go-round. In a slightly rotating universe on vast scales beyond galaxy clusters, that spin could impart a small outward acceleration to matter. Poplawski suggests what we call dark energy might actually result from this cosmic spin, a kind of inertial push driving galaxies apart. Importantly, if the universe is closed, meaning finite in volume and rotating as his model proposes, then as space expands, the spin would slow, like an ice skater slowing their spin by extending arms. And here's the most intriguing part. As cosmic spin slows, the outward centrifugal force diminishes accordingly. In other words, dark energy's effect would gradually weaken over time. That's a fascinating coincidence, given DES observations indicate dark energy weakening of exactly this nature. Poplawski's rotating universe concept ties into another bold idea, black hole cosmology. He proposes our universe might have been born from a black hole in a parent universe. Going further, this suggests every black hole could be a gateway, creating a new baby universe beyond its event horizon. In this scenario, the parent black hole spin is inherited by the baby universe, and thus our universe's preferred axis might simply be the spin axis of the black hole where our universe formed. This is a wild and captivating notion. If true, it means our universe exists within a cosmic family tree, a multiverse connected through black holes. Spin provides a natural explanation for dark energy, and the multiverse provides a reference frame for that spin beyond our universe itself. Does this mean our universe will eventually stop expanding and collapse? The rotating universe model in itself doesn't guarantee a big crunch. Its main achievement is showing how dark energy's observed weakening could be explained without exotic new particles, purely through geometry and motion. However, if dark energy generated by spin continues fading, this could very well lead to slowing expansion. A closed, rotating universe might reach maximum size, and then, depending on its total mass and energy, could contract. The axion dark energy model and the rotating universe hypothesis both attempt to explain the clues we're observing. They offer vastly different visions. One adds a new ingredient to our universe's recipe, axions plus a lambda twist, while the other rewrites space's very architecture. Yet they share a common thread, the idea that dark energy might not be a simple, constant force after all. It could be just a phase in the universe's history, a changing phase that ultimately reaches its end. And if that's true, the long-term future of the universe could be fundamentally different from the endless expansion we once imagined. The implications of a finite lifespan for the universe are profound. For over 2 decades, lambda CDM, with its unchanging positive cosmological constant, has been cosmology's foundation. If dark energy truly evolves, this foundation needs reinforcement or revision. From a scientific standpoint, confirming dark energy's evolution would urgently force theorists to update our fundamental models. It could involve an ultralight axion field interacting with gravity, a modification to general relativity itself, or some other unknown quintessence field. A negative lambda, if confirmed, would mean that in the long run, our universe resembles an anti-de Sitter space, a geometry with a natural tendency toward contraction, favored in theoretical physics, for instance in string theory, but previously thought irrelevant to our actual universe. This could open possible connections between cosmology and quantum gravity, as physicists still struggle to understand how vacuum energy could be below zero. And then there's this existential angle. We humans are living in a universe that might be middle-aged. Sure, 33 billion years is unimaginably long, far exceeding the lifespan of the Sun, Earth, or even our galaxy in its current form. But in principle, a finite universal lifespan means there's a cosmic deadline. This matters for space exploration and colonization, even on timescales dwarfing human history. Many futurists imagine that life, if it lasts long enough, could spread to other galaxies over trillions of years. In an eternally expanding universe, distant colonies would eventually become isolated, because accelerating expansion outpaces even the fastest spacecraft. But in a recollapsing universe, those distant journeys might someday be assisted by the universe itself. This is speculation, of course, but understanding the universe's long-term structure could be a game changer for such grand ideas. Before getting too excited, it's worth emphasizing once more that arguments for the Big Crunch are based on data still being collected. Results from DES and DESI need verification. Upcoming missions will be pivotal. Euclid, the European Space Agency space telescope launched in 2023, is surveying billions of galaxies up to 10 billion light-years away, mapping how dark energy's influence has changed throughout cosmic history. NASA's Nancy Grace Roman Space Telescope, scheduled for 2027, will refine measurements of cosmic expansion with extreme precision. These observatories, along with ground-based projects like the Vera C. Rubin Observatory, will confirm or refute the subtle trends being observed right now. Within a few decades, we'll know whether dark energy's power is truly diminishing, and if so, how quickly. The universe's fate could shift from an eternal philosophical question to a solvable scientific problem with a data-driven answer. We began with a stunningly simple possibility. Our universe has an expiration date, 33 billion years from its birth. Now we've seen how this idea emerges from the faintest clues, tiny anomalies in how galaxies cluster and how light travels over billions of years. We've always gazed at the stars, wondering about eternity. Now we must consider that eternity itself might be shorter than we once thought, and if all answers point toward an ending, they also raise a new question. Could anything be done to change the outcome? Could intelligence, however advanced, find a way to survive the universe that birthed it? Could future beings somehow escape our universe's collapse? Perhaps by leaping into a neighboring multiverse or creating universes of their own? Or will the final singularity,